So in the last lecture, we discussed about the induced voltage and induced torque in a DC machine, and we also derived the power flow diagram. Now we'll be starting with the types of DC machines, and we'll start with the DC motors. So DC motors, despite the increased use of AC and AC motors, like induction motors, there are still some applications where DC motors are preferred, like in case of traction. And even if we talk about nowadays, we are again switching towards HVDC systems. DC is again gaining some popularity because of our electronic conversion devices, and because of this, because of certain advantages associated with DC motors, they are finding some use still in a lot of industrial and commercial processes. And as far as DC motors are actually concerned, they are actually depending upon their speed regulation. We actually compare them. Uh, so, what is speed regulation? Speed regulation is simply the ratio of the ratio uh, V omega at no load minus omega at full load divided by omega at full load. And if we want to find this out in terms of percentage, we can multiply it with 100%. So this basically is a rough measure of the behavior of the DC motors, speed, torque, performance, how exactly the motor, how exactly the speed of the motor will fall once it is loaded. Say for example, it's running at full speed, so and at no load, obviously the speed will be higher. But as soon as we load it fully, obviously the speed will fall. The motor, as soon as we load the motor, the speed of the motor basically falls, and this difference measured in terms of the rated full load speed of the motor is known as speed regulation. If this if there is a positive value of the speed regulation, that means omega no load minus omega full load is positive. That means basically the motor speed falls as the machine is loaded. If the speed regulation is negative, that means omega full load is greater than omega no load. That means the motor speed increases with the increase in load. Fine. So depending upon the type of load, that can actually the speed regulation can be positive and negative. And how quickly this speed will fall, that actually gives us a measure about the performance of this uh, motor, and how much the speed will fall as soon as it is loaded. Now we'll be taking up, as I have been saying regularly, 5 different types of DC motors. So positive speed regulation means as soon as you are loading the DC motor, the speed will decrease. Negative speed regulation means as soon as you are loading the motor, its speed will increase. Fine, and that will actually depend upon the type of load you are using. And also this speed regulation, how quickly it falls, how much it falls, that actually gives us that actually determines the performance of the DC motor and a measure of its speed torque characteristics. Now we'll be looking at 5 different types of DC motors. One is the separately excited DC motor. Two, we have the shunt DC motor. Three, uh, the permanent magnet DC motor. Before that, we'll actually study the series DC motor. Fourth, we have the permanent magnet DC motor, and fifthly, we'll be having the compounded DC motor. So it can be an over compound or an under compound DC motor. So we'll be discussing each of these types in detail regarding their speed torque characteristics, the equivalent circuit of these different types of motors. Now starting off with the equivalent circuit of a DC motor. So as far as equivalent circuits go, the electrical machines are basically electromechanical devices. They consist of a number of windings and rotating parts. So these windings, the resistance, the inductance of these windings can be combined. The leakage, the magnetic parts that were actually involved in the circuit, the flux, the leakage flux, all of these can be actually shown using electrical equivalents and such as simple resistance, inductance, voltage, current, etc. We'll be actually using this equivalent circuit approach in all the machines that will be studying, the transformers, the induction machines, the synchronous machines, as well as the DC motors. So what these represent, they simply represent the total behavior of this machine, of this electromagnetic of the electromagnetic principles that are involved in this machine. There may be drops that can be represented in terms of resistance. There can be flux drop, flux leakage that can be represented in terms of inductance, and the internal resistance of these windings, etc. So these can be represented by electrical quantities. As such, they will be known as equivalent circuits. So first of all, starting with the DC motors, what we have is we can basically represent the armature circuit and the field circuit. The armature circuit will basically be represented using a resistance, RA. So what is RA? RA is the internal resistance of the armature windings. So we have seen there are a number of windings, number of conductors found on the armature. So the total resistance of that is shown through armature resistance, as well as the resistance that leads to basically voltage drop in the brushes. We can actually show voltage drop using a DC source as well. But instead of doing that, since this voltage drop is as we have studied, the brush voltage drop is of the magnitude of 2 volts, we can actually neglect it here, and that can be actually taken as a part of the armature resistance itself, and you have the internal generated voltage of this device that is shown by EA. So this circuitry here represents your armature resistance, fine, armature circuit. It will also have its own inductance, but since DC current is flowing in this circuit, so we'll assume that inductance is basically going to be shorted after some amount of time, and you will be applying terminal voltage to this device. So since this is a DC motor, you are actually applying VT because of the internal resistance of the windings, the voltage drop So the brush is extra. There will be some amount of voltage drop equal to IARA. So your EA, that's actually the internal generated voltage, that's also given to us. We know EA is given to us by equation K phi omega. So this voltage EA will be equal to VA VT minus IA RA. Fine. So since we are applying the terminal voltage, VT will be greater than EA, and the armature resistance across the armature resistance there will be a drop equivalent to IARA. So this equation is validated. This represents your armature circuit of the machine. Similarly goes for the field circuit. Field circuit also has windings. Since the field circuit is also producing armature flux, so we'll be basically representing the field circuit using a series combination of RF and LF. RF basically represents your internal resistance of the field internal resistance of the field windings of the DC motor, fine, as well as in this case you have the inductive part represented by LF. Since the field coils are responsible for generation of magnetic flux, and sometimes we can actually also incorporate an adjustable resistance in series with the field resistance, so that we can actually change the magnitude of IF flowing through the circuit. By changing IF, we can basically control the flux produced by this machine. So greater the resistance, lesser will be the so depending upon what will be the voltage that you will be applying to this machine. So if VF is constant, if the DC voltage that you are applying to this machine through the field windings is constant, if you increase the value of the resistance, the field current will decrease. That means your flux will also decrease. That means your internal generator voltage EA will decrease across the armature of the circuit. So if you decrease the value of R adjacent, that means R adjustable, that means you are decreasing the field resistance from the previously mentioned value. So you can basically increase the value, you can basically control the value of IF by changing this adjustable resistance by means of a rheostat. So this here represents our and we can actually represent the field circuit as simply equivalent to IF RF plus IF R adjacent plus LF DIF by dt. Fine. So again, if the field current is constant, more or less you can ignore the you can basically be able to show LF as a short across this field winding. So there are two equations here, two voltage law equations, one representing the armature circuitry given by EA is equal to VT minus IARA, and secondly on the field winding side you have VF equal to IFR adjustable plus IF into RF plus LF DIF by dt. So these two equations this is the basic form of the basic equivalent circuit of any DC motor. Now in case the field windings are, in case it's a separately excited DC motor, that means basically the field windings and the armature windings are separate from each other. So this will be your equivalent circuit. In case it's a shunt DC motor, the field windings are basically in parallel with the armature winding. So you can basically show RF in parallel with RA there. In case of a series DC motor, the field windings are in series with the armature winding, so you can show RF in series with RA. And in case it's a compounded DC motor, then it can either be a short compound or a long compound, that we'll be seeing later on. And there will be a mechanical part here that is actually rotating, for which we'll be having mechanical quantities determining the motion, equations of motion. These quantities will be simply the moment of inertia and the viscous friction coefficient J and B. Also, the induced torque in this machine that we have already derived, torque induced will be equal to K phi IA. Fine. Now, before we study the different types of motors in detail, we will understand the magnetization curve of a DC machine. So magnetization curve of a DC machine is simply the plot between the internal generated voltage EA and the field current. It's a plot between EA versus IF. Fine. Now internal generated voltage we know is equal to K phi omega. So if we say omega is constant, in that case EA is proportional to the flux of the machine. Flux of the machine is basically generated by the field windings. Fine. So we know here, as already told you before also, so greater the IF, greater will be the flux, greater will be the EA. Lesser the IF, lesser will be the flux produced, lesser will be the EA. So therefore, and since flux is proportional to IF, you can say EA, therefore EA is proportional to IF. So this is EA, this is IF. So there will be a linear relationship between EA and IF since they are directly proportional. Now, after some time, what will happen? But the increase in flux will be no longer possible, even if we increase the magnitude of field current IF. The machine basically achieves saturation. As we know, there is a magnetic saturation beyond which flux will no longer increase in the machine. Since flux will no longer increase in the machine, that means EA will become constant now, irrespective of increased IF in this in the field windings of the DC machine. So this here represents our magnetization curve, and what happens is basically after some amount of time, all the domains are aligned in one direction. No longer the machine has achieved saturation. Increase in flux is no longer possible after that. Once the magnetic saturation occurs in the system, once flux is no longer increased, even if we increase the IF, even if we change, even if we increase the voltage fed to the field winding so that IF can be increased, that will no longer affect the flux in the machine because it has already achieved saturation. And what we do is we basically tend to operate the machine near to the saturation point so that maximum amount of power and speed can be basically obtained from the DC motor. Since we know EA is proportional to flux, so greater the flux, greater will be the internal generated voltage in the DC machine. Now let's start with separately excited and shunt DC motor. We'll be studying both these two together because more or less their torque speed characteristics is almost similar. As I said to you, a separately excited DC motor will basically have separate field windings, so you can basically simply show a separately excited DC motor using the equivalent circuit of the DC motor that we just draw. This will be the equivalent circuit of a separately excited DC motor. So this is your separately excited DC motor. In case of uh, shunt DC motor, I said the field windings will actually be in parallel with the armature winding. So if this is our field windings, this will be our armature winding. So armature windings and the field windings are basically in parallel. The armature winding, this is your field winding. So IA will be flowing through here, IF will be flowing through here, and this total current will be the load current of the DC motor. So looking at the two diagrams, this is a separately excited DC motor, the field windings and the armature windings, they are separate from each other. In case of shunt DC motor, the field windings and the armature windings, they are in parallel with each other. In this case, we can note simply IF will be equal to VF divided by RF as we achieve saturation. LF will be LF will no longer LF will be shorted, and the terminal voltage VT is equal to EA plus IARA, or you can say EA is equal to VT minus IARA. So this is your equation for the separately excited DC motor, as well as the load current in this case will be simply the armature current. Now in case of a shunt DC motor, you can see IF in this case, the current that is flowing through this path, through the parallel path, through the field windings, right? It is equal to the voltage across it, that is Vt, divided by the resistance of this winding, that's Rf. Now in case of shunt DC motor, you can see you are only using one DC source, one DC power supply to feed both the field windings as well as the armature windings. In case of a separately excited DC motor, you will have to use two different DC voltage sources. This is your IF equal to VT by RF, and VT in this case will be equal to EA plus IARA. That equation will not change. That's why I said the torque speed equation will also be more or less the same. VT is equal to IARA because the voltage across this point, these 2 points is also VT, and the voltage across this point and through here is also VT because they are all in parallel. But in this case, the load current IL is equal to IA plus IL. So you can see a separately excited DC motor is supplied from a separate constant voltage power sources, DC power sources, while in case of a DC shunt motor, the field windings and the armature windings, they are fed from the same source. Now we'll draw the terminal characteristics of the shunt DC motor first, and then the separately excited DC motor. Terminal characteristics of a shunt DC motor. So what is the terminal characteristics? Terminal characteristics, as the name itself implies, terminal means the output of the machine. So whatever output quantity of the machine there are, will be plotting them against each other. That basically represents your terminal characteristics of any machine. So in case of the DC motor, what are the output quantities? The output quantities are basically the torque and the speed. In case of the generator, the terminal quantities are the voltage and the current that are actually generated. But in case of motor, the output quantities are the speed and the torque that is produced, and that will be actually used to feed the load in this case. So we'll be basically plotting the torque versus speed characteristics of this machine. So this terminal characteristics of a shunt DC motor, they are also known as the speed torque or the torque speed characteristics of a DC motor. Fine. So how the DC motor will basically, how the torque will actually vary with respect to the speed of this motor. What are we actually need to first of all derive the speed equation of the shunt DC motor. Let's derive the speed equation. We know for a DC motor, a shunt DC motor rather, Vt is called Ea plus Ia Ra. Fine. Now keep this figure in your mind. Vt is the voltage that you're basically applying to this DC motor. It is not the output voltage in this case. Vt is called Ia. Vt is called Ea plus IaRa. And also know the direction of currents. These direction of currents for a DC motor is into the armature, whereas in case of the generator it will be out of the armature, and we'll be basically doing that. Vt in this case is Ea plus IaRa. Now we know Vt, Ea is equal to k phi omega, therefore Vt can be written as k phi omega plus IaRa. Fine. And also we know torque induced in a machine is equal to k phi Ia. So therefore Ia can be written as torque induced by k phi. Therefore what will happen to this equation? Vt is equal to k phi omega plus torque induced divided by k phi into Ra. From here we'll actually find out omega. So what is omega be equal to? Vt minus torque induced divided by k phi Ra, and with omega there was also k phi, so this will be dividing all this, so 1 by k phi. Fine. Or you can also write it as Vt by k phi minus torque induced into Ra divided by k phi. Yeah. So this is our speed equation, omega equal to Vt divided by k phi minus torque induced into Ra divided by k phi square. So this equation basically relates our omega with respect to the induced torque in the machine. So if we plot this equation, torque induced and versus omega, what will we be getting? This is our omega. is our induced torque. So you can change from you can take T induced equal to 0. So Vt divided by K phi. So if you are applying, say for example 200 volts, K will be using the number of conductors, the poles of the machine. Can calculate K. Some flux will be produced by the field circuit. So there will be some volt, some speed of the machine at torque when torque induced is equal to 0. So as T induced increases, this graph will now start decreasing, because this quantity increases as torque induced increases. So that will basically be subtracted from Vt by K phi. So this is your maximum value where your omega is equal to Vt divided by K phi. So this is your torque versus speed profile for a DC shunt motor. And what we have done is, in this case, we have actually assumed all other quantities to be constant while plotting this graph. We are only varying torque induced and seeing how omega will change with respect to torque induced. We are actually assuming all other quantities in this system for the time being are constant. But there is one important quantity that we need to take care about, and that is the armature flux of this machine. So what happens with armature flux? We know that armature flux causes flux weakening in this machine. So flux basically will decrease. So if flux decreases, that means Vt by K phi will increase. Fine. And again, in this case, flux is actually on both sides. Flux will increase, flux will decrease, Vt by K phi will increase. So with armature reaction, what will happen with armature reaction? With armature reaction, we have understood there is flux weakening. Flux weakening means phi will reduce. If phi reduces, we have to plot now omega versus torque induced. That means once you plot this and knowing the value of flux, this is without armature reaction taken into consideration. Flux decreases, omega will basically increase. That means this graph will basically deviate like this. So this will be the value of this will be the torque speed profile of an induction machine with armature reaction taken into account. What happens with armature reaction is the flux reduces, but with reduction in flux, the motor speed at any given load will basically increase. Now, if we have a compensating winding attached with this DC motor, we know that with the compensating winding, we can basically make the flux of the machine, the flux weakening will basically be neglected. In that case, we'll go back to the original torque speed characteristic that was actually without the armature reactions. Uh, so this is your graph for the terminal characteristics or the torque speed characteristics of shunt DC motor. We can also explain this like this. So what happens here? I'm giving a step by step. Say for example, we are increasing the load. Increasing load. Increasing load means T load will increase, and that will become actually greater than the induced torque in the machine. Fine. So this is your load that's actually applied to the shaft of the DC motor. This torque is basically applicable to the shaft of the DC motor. This is the electromagnetic torque that's actually induced in the DC machine because of the electrical and magnetic principles. That simply torque is called K phi into IA. That torque that we are talking about. So, so once this happens, torque load is greater than the induced torque in the machine. That means naturally the response is speed decreases. So as speed decreases, EA, which is equal to K phi omega, also decreases. Fine. So EA also decreases. As EA decreases, now we have IA equal to IA of a DC shunt motor. Looking at the equivalent circuit, what will be the IA of this DC shunt motor if VT is equal to EA plus IRA? IA will be equal to VT minus EA divided by RA. VT minus EA divided by RA. Now EA is decreasing. So if EA is decreasing, VT minus EA will increase. That means IA will increase. If IA is increasing, torque induced, that is equal to K phi IA. IA is increasing, that means torque induced will now increase. So torque induced will increase and become equal to the load torque of this machine. So this is the balance which at all times under a steady state condition, the load torque of the machine should match the electromagnetic torque that's produced in the machine. So this is actually true for all types of machines, and so this uh, goes back to its this goes back to where it so before increasing the load, this was the case. Torque load was equal to torque induced. But then we suddenly increase the load, and then basically this phenomenon takes place. So torque load now becomes again equal to the induced torque, but at what cost? At a reduced cost of reduced speed. Fine. So with increase in load, the speed decreases, but the motor finally settles down again at a new value of it finally settles down at a new value of speed, but that's actually reduced. But this load torque and the induced torque will now again be equal after same amount of time after achieving that balance. So this is your terminal characteristics of a DC shunt motor, and the terminal characteristics of a separately excited DC motor. We'll actually do that in the next session now. Yeah, fine. That's all for the session.